Hi there, this is another look at matrices, and now looking at matrices to solve equations. You'll note up here actually in this, these are simultaneous equations which you've seen before, but unusually this is three simultaneous equations, and we've got three because it's x, y and z. So you don't often get this at GCSE. I'd be surprised if you saw it much at all. But notice it's more complicated, and it's not surprising then that we really want a new method to do it. Now, on the new Casio calculators, you can actually tell it to solve these. These are called, if you like, I was going to write cubic, it's not cubic, it's like 3x3 simultaneous equations. So you can tell it to solve those, but normally when we get more and more complicated simultaneous equations, for instance, you could get theoretically 4x4 or 5x5, we can use matrices to solve them. And this is the matrix equation for the equations you've got over there. You can see it's quite obvious. You've got 1x, so it says 1. It says minus 2y, so we've got minus 2. And we've got 3z. And you do the same thing for all the equations. And of course, when you times that top row by this first column, you would get x minus 2y plus 3z. Notice it says equals 4. And over here it says equals 4. So that top equation really is all just put into this matrix equation and second equation and third equation. So I want you to do the same thing for these. I'm going to pause or get you to pause the video for me. Try to write these matrix equations out, and then we'll have a go at them. And if you're not sure what to do, here's the answer to the first one. Hopefully you can go back to it. So now I want you to try pause the video and do them now. Okay, hopefully you've done that, you've got them all right. Here's mine and the other three as well. Okay, so fingers crossed you can do those. We're going to try to use matrices now to solve these two equations, and it's a bit daft really because we know a variety of different ways to solve these. But I'm going to use matrices to do them anyway, just to show you the method, and then we'll extend to 3x3s. So notice here, I'm going to write these in the matrix equation form. I've got 5 of those. Minus 1. How many? Oh, these are written the wrong way around, just to confuse you. You've got minus 3x, and you've got plus 2y. That is times by xy, and the answer is 14 minus 14. Okay, that's fair enough. Notice then, I want to effectively move that onto the other side, and then I'll know what xy is. The way we do that, of course, is we are going to left multiply over here by the inverse of this 2x2 matrix, and you can think of it as moving over effectively, and when it moves over it becomes, because I've got it on the left, I'm going to multiply on the left. I multiply by the inverse, 14 minus 14. Now what is the determinant of this? I'm just thinking that's 10 minus 3. So I think the determinant is 7. This is the determinant equals 10 minus 3 is 7. So my answer will be 1/7 of, now they switch places, 2, 5, and these change signs, so they just become 1, 3. 14 minus 14. And if I do this, it becomes 1/7 of, 2 14s are 14, effectively it's 14 that, and 3 14s are 42, minus 7, I reckon minus 28 when I do that. Just check those. I might have some dodgy maths going on. The 7th of 14 is 2, and the 7th of 28 is 4, so it's minus 4. And I suppose I shouldn't finish off by writing x equals the first one. Yeah, like that. X equals 2 and y equals minus 4. So relatively straightforward. Notice the use of the inverse matrix when you move over. Here's a different equation. I've only thrown this in. It's not simultaneous equations, but it's highlighting to you what you do. So m here again, I want to move this one over, but this time it's on the right. So don't be surprised. We've got to right multiply now. We've got to multiply by the inverse on the right. What's the determinant this time? You've got to find the determinant, or else you're always going to get them wrong. 2 minus 1. After saying that, it's 2 minus 1, which is 1, which is the perfect one. So you don't have to do much with that at all. So anyway, therefore 1, 3, 3, 2. I can ignore the determinant division because it's 1, and I can just switch these around, 1, 2, and these become minuses. And I've found the inverse. Now I multiply. That's 1, that's minus 3, I reckon minus 2. So 2 by 2 by a 2 by 2, so my answer will be a 2 by 2 this time. Minus 1, I think that's 5. That's 3 minus 2 is 1. Minus 3, I think that's 1 as well. So that's what I think it is. Good, it is. So far, so good. We're on to the 3 by 3 matrices. Now, these are simultaneous equations again. So if I'm going to solve this, I need a matrix equation. 4, 1 minus 1. 3 minus 1, 2. 4, notice, I need a 0. Times by x, y, z. And that's equal to 12 minus 1 and 17. So if I move it over, the x, y, z is equal to, it's on the left, so I'm going to find the left inverse matrix. Yeah, I'm going to multiply on the left side. 3 minus 1, 2. 4, 0 minus 3. Inversed. I'm going to times by 12 minus 1 and 17. And of course, that allows me now to find the inverse matrix. Now, this should be done really on the calculator. You don't want to be doing that in your head if you don't have to. And there's no K's or funny algebra there. So I'm just going to type into my calculator. I'll pause the video and I'll come back. So this, according to me, is 3/25 here. Of course, I've done it on the calculator, so it's gone to decimals, but you can still see it on there. So what's that? 1/25. And I've got next one is 17/25 minus 8/25 minus 11/25 4/25. Should have just taken out 25 as a common factor. I think they're all going to have that there, but that's where the calculator's done it. 4/25 and minus 7/25. And of course that is still got to be times by 12 minus 1, 17. So I'll pause the video again and times it and get an answer. And according to me, when I've typed that in, it took me a while actually, I've got 2, 1 and minus 3. So again, I should write out x equals 2, y equals 1, let's see what I've done, and z equals minus 3, so I'll agree with that. So notice the way you're meant to write it, that finishing line, as you would with normal simultaneous equations. Now what I need to show you now is the fact that when you get 2 by 2 simultaneous equations, this is what normally happens. You normally have a line, and they cross in some place. This is graphically what it looks like. And I don't know what this equation is. This looks as if it crosses at minus 4. And it goes up in 2's, so I reckon this is y equals 2x plus 4, minus 4, sorry. And this one, I'm crossing at 1, 2, 3, 4, positive 4 this time, and it seems to be going down with a gradient of minus 2/3 actually. It's got y equals minus 2/3 of x plus 4. But what you're doing is we're saying basically if you solve these two equations, they will cross there. You'll get this one solution. It's called a unique solution. There's no doubt about it. It's a unique solution. And this one, interestingly, you notice I've got two lines here. I've got 6x plus 10y is 60 and 3x plus 5y is 15. And look, I'm saying when do these lines cross? That's really what this was. When do these lines cross? Here. When do these lines cross? Well, actually, they never cross. And so one way of saying this is there's no solutions. There's certainly no unique solutions, which is the way we tend to describe it at this stage. Now, if you look at the matrix of this, so I've got 6x there, and I've got 10y, and I've got 3x, and I've got 5y. What you notice actually is one is a multiple of the other. Then xy is equal to 60 and what is it, 15. But what you'll notice is if I find the determinant of this matrix, I get 30 minus 30, and this is what we'd call a singular matrix. It's equal to 0, and it's one where it has no unique solutions. And this turns out to be the rule. If you have a determinant that is equal to 0, you won't get a solution. But if you get a determinant which is not equal to 0, you will get a solution. And we can carry that forward into a 3 by 3. Now what you need to understand is when you write in a 3 by 3, we actually get a plane. I'm going to show you that using an autograph very briefly. So I'm going to not pause the video, but I'm going to just see if I can get this to work. Bear with me. So I've already typed into this. This is a package called autograph, and I've already typed in one equation with three unknowns: x plus 2y plus 4z is 1. And this is what I mean by it's a plane. You can probably see this. I can rotate this, and you can see that there is a plane. The autograph's quite clever. It just draws it in the box, but it actually goes on forever and ever and ever. So I shall type in another equation, and this time I'm going to type in 3x plus y plus 2z is equal to 1. And it's come up there. And now you can see I've got two planes, and you can see they actually cross. You can see how they cross, and the great thing about this is I can rotate it. You can see how these cross. They're almost like two planes like there. Normally we might show them like that, or you've definitely got two planes. And I'm going to type in a third one because I've got a third I'm going to type in. And the third equation is going to say 8x plus y plus 2z and equals 2. Well, I typed in equals 1 equals 2 there, and there it is. And notice what you get. It seems to me, well, it's quite tricky to see what's going on. Let's change that last number. I want to change that last number, I think, to a different number. It might just make it a bit easier to see. I initially typed in 1 by mistake, and this time I'm going to do the same thing. I'll type in -1 just to see what happens to my equation. And look at that. I was just able for a moment there to see all the way down it. Can you see all the way down that little hole there? And these, I don't think these cross in quite the same way as before. I don't think there's any point there. You can see all the way down. There's no point where you get one specific place where they cross. Let's pick on a different one. So I'm going to change this equation so that it is a different number. I've just typed in that as 3z. I'm just wondering if now they cross. It's hard to see really. They might all cross here, you know. So someone's done this. They do seem, so you can, one thing you can do is you can say highlight them all. There, and that one. And you can ask it to find a point where they all cross. Intersection, that's what it is saying they do all cross. So that is a point where all three planes rather cross. So I think that's quite nice. Now we go back to what we had here, and I just carry on. Now what this is highlighting then is when you have three planes crossing, there's a variety of different ways they can cross. They can cross, well, they can not cross at all. You've got three planes which miss each other. You can get three planes which don't cross it. And it's actually quite difficult to find three planes that do cross, it would seem. The key again, once again I'm saying the key again here is the fact when you do your matrix equation, we are looking for, let's go back to that. We are looking for the determinant, and if the determinant is 0, you'll get non-unique solutions. But if the determinant is not equal to 0, you will find a unique solution like that one. So just going to quickly do this one. Matrix equation for this is 2 minus k minus 3. Obviously it's times by xy, and it equals, according to this, 6 minus 2. So it says these equations do not have a unique solution. So because it's non-unique, I can find the determinant of this, and that must equal 0. So if I do that, I get minus 6. I think plus k squared equals 0. If you do that, so k squared equals 6, or k. When I square root 6, which I will do, I get two answers, plus or minus. In lessons, is that the answer? Yes, it is. In lessons, we need to next look at this one, and this is a big old question. And this is how we solve problems of, this one says it's not got a unique solution again. So again, I know its determinant will be equal to 0. It's just what happens next. So best of luck with this. In lesson we'll do a bit more, but I hope that's a good starting point for us.